This is really an intervention design. So I won't be specifically talking about an experimental design. This is an intervention design. And it's involving AI, artificial intelligence. But I'm going to talk, our entire team's goal is so that you can design these types of interventions. Use your expertise to design these. So I'm going to talk about this problem in a way that I hope will help you do this design. So we're going to talk about JITAIs, personalizing JITAIs. Of course, you got to know what is one, so we'll worry about that first. And then this is all about digital interventions, or it can be an intervention that's delivered by a wearable or by your iPad in the case of, say, an older adult, Siri, or it could be on your phone. It just depends on the particular mechanism that's required. And these interventions involve an algorithm that's running as the intervention is being experienced by the individual. And we're going into the field hopefully soon in my waves with one of these interventions, and I'll talk about that. So just to remind you about JITAIs, Billy spoke about a JITAI, and she was talking about a digital intervention in which every day the person would report how they were doing in terms of their substance use, and a risk score would be formed, and then if their risk was high, they'd get some sort of behavior change message. Here's a different kind. There's a JITAI that is tailored to the individual. It uses, again, a decision rule. In this case, the tailoring variables might be the time of the day, how engaged they are with the intervention, whether or not they've been using cannabis recently, and it outputs an intervention option. In Billy's case, that was a behavior change message. Now, in terms of JITAI, I'm going to be talking about a JITAI, personalizing JITAI. So the key thing to understand is when you implement a digital intervention that operates according to decision rules, i.e. the person's at high risk, send a message, for example, these decision rules are the same for everyone. So if Danny and I are in the intervention and we both have the same time of day, our level of engagement is the same, and our recent cannabis use is the same, then we're going to get the exact same type of message. So the decision rule would be the same for Danny and me. In this case, if I start to respond, if I'm less responsive to this decision rule, Danny's more responsive, it doesn't matter, we still get the exact same thing. So what is a JITAI? A JITAI acknowledges the fact that Danny and I would be subject to the exact same decision rules if it was a JITAI. So in a JITAI, it provides a second layer of adaptation using our responsivity to the digital intervention in real time as we experience it. So am I changing my behavior when you provide me different types of behavioral support or not? And how should the decision rules adapt to those changes? So there's two aspects to JITAIs. The first is that the decision rules are not deterministic, they're probabilistic. So, for example, before I said if an emergent, on the last slide, I said if the emerging adult's recent cannabis use is high and the current time is morning, then send a behavior change message. Here, it's probabilistic. So I would only send that behavior change message with probability 70% of the time. And there's a variety of reasons why you might be interested in this. Often we don't want to overtreat, we don't want to induce habituation to too many stimuli. So you might want to use a probabilistic decision rule for that reason alone. So what do JITAIs do? They take advantage of one using a probabilistic decision rule to change this probability depending on how someone is responding. So let's say, for example, that Jane's data indicates that she is responsive in the morning when she's been recently using cannabis. So then the probability might increase above 0.7. Or if Jane is less responsive in the morning when she's been recently using cannabis use, the probability would decrease. So you'd provide the intervention with a lower chance. It's moved according to their responsivity to the messages. So these algorithms, they have two elements. This is always the case. Okay, so if someone comes to you and they tell you they're using ChatGPT or they're using deep learning or whatever, in our mind, we just need to remember there's two parts here. The first is a learning algorithm, which is an algorithm. It's usually some statistical method like a large language model used in artificial intelligence or deep learning, whatever. I mean, it's a free world, they get to do that. And this algorithm incrementally updates estimators of parameters in a model for the desired behavior. For example, engaging in the intervention or reducing substance use, that might be a desired behavior, proximal outcome. It has a model. This algorithm maintains some sort of model. And in the example I'm going to show you next, it's going to be a linear model. So it's something that we can immediately, and I can clearly explain at this moment in time. But you could have very complicated models as well if you have a large amount of data. Okay, in our case, in the algorithms, we develop our models are all, we use Bayesian methods, and I'll explain what I mean by that shortly. The second element of these algorithms that alter the probability according to our responsivity to the different types of behavioral messages is an optimization algorithm. And this algorithm takes the estimated parameters that were estimated in this first part. Again, this could be a pretty complex method like deep learning, or it could be a linear model. It just depends on the amount of data you have. It takes these estimated parameters and it uses those estimated parameters to optimize the choice of intervention option. Should a behavior change message be sent right now, or should we just not bother the individual, for example? In our lab, what we use is posterior sampling, and this is associated with Bayesian statistics. What we do is we calculate, given the data that's been seen so far, what's the probability of a particular intervention option being most effective. We take that probability and then we use that instead of 0.7. So I'll show you an example. So here's my math. Here's our math. So we have a proximal outcome in Billy's setting. I think it was substance use on the following day, right? Here it might be your intervention engagement after a particular time at which you could be delivered a message. So did the person go to the app? Are they self-monitoring? So on. So this is our outcome that we're really trying to impact. We have tailoring variables, and the tailoring variables I gave on the prior slide have to do with recent cannabis use, whether or not they've been recently using, for example, like in the last 12 hours. And then the current time of the day. Is it early in the day? Is it later in the day? And then we have an indicator of whether or not we send the behavior change message versus we don't. So I've made this really simple so that I can do a good job explaining it to people. And what we do is we take this outcome and we use a Bayesian method. One could use a Bayesian linear regression model for this outcome. So this is something most people are used to. I mean, if you do applied statistics with your data sets, you often fit linear regression models for probably, most likely, much more sophisticated models. So here's a really simple model. I have my outcome, which is a measure of engagement after the decision point. The intervention. So we were looking in the morning. In the case of my waves, it's twice a day. So this is level of engagement. And then you have the regression coefficients, that's the alphas and the betas. And remember, A is 1 if if the algorithm provides a suggestion, the app sends a suggestion, versus 0 if the app doesn't bother you. So what that model implies when you write a model like this is it implies that if this term in parentheses is greater than 0, then it's going to send a behavior change message. And this is great. So if you knew these parameters, you would just look to see if this term is 0 is related to the two tailoring variables, recent cannabis use, whether or not it's in the morning. If you knew this entire model, all the alphas and the betas, you would just look to see if the sign is greater than 0, and that would tell you whether or not to send a message. Really fantastic. Of course, in real life, we don't know those regression coefficients. compositions, right? We don't know those. We call them weights. We don't know the betas and alphas. And so what are the ingredients in this online? Remember, the first element is online learning algorithm. What are the ingredients? A model. Here's an example of the model. There's a prior distribution because we're using Bayesian statistics. This is actually fascinating. I just want to tell you, the prior distribution is a place to put a lot of behavioral science expertise. It's really exciting. This is a very exciting area to form the prior distribution. So it's one's expertise related to the efficacy or the usefulness of this material, as well as the behavior change message.
Yeah. Care if this linear combination is significantly different from zero?
No, I don't care. That's not related. So what's going to happen is this learning algorithm is going to estimate, well, it's going to use the Bayesian approach with these three ingredients, and it's going to produce a posterior probability that this quantity is greater than zero. So it won't produce a hypothesis test. We're not going to test anything with alpha equal 0.05 or twice a day in my waves. It's not happening. Twice a day in my waves, what's going to happen is the algorithm will produce a posterior probability that whether or not it's worthwhile. That's what's going to happen.
That's a great example of the difference between what we call conclusion priority and decision priority thinking. So we've all been trained as scientists to think in terms of drawing conclusions about whether a particular parameter is different from zero or something like that. But when you're optimizing an intervention, you have to make a decision about what's going to go into the intervention. So it's you use data, but it's a different way of approaching data.
Right, and the basic for what Linda's talking about, because it gives me the probability that the evidence is supported. Is the prior evidence on the individual and potentially other individuals supported that it's worthwhile to send a message in this context, in this setting?
But maybe is that the focus is on decision making as opposed to gathering scientific information to make statistical impacts or any scientific inference.
Yeah. On decision making in the moment as the person is experiencing the digital intervention. We don't want to bother them if the evidence is indicating it's not worth it to them. I mean, it's just, you really don't want to bother people as they go about their life if the evidence is not in favor of that. So here's our three ingredients. The data you have so far up to that time point. Again, at my waves, it's 2 times a day. You have a prior distribution, which again is quite interesting way to bring in, but behavioral expertise. That's one of the things I'm really excited about. And then you have some modeling. We have a simple linear model. And all of this together produces, if you use Bayesian linear regression, it produces a posterior distribution. It gives you a posterior probability that it's effective to send a message in that current setting. With these values of time of day and whether or not they've been using cannabis in the prior 12 hours. You calculate that posterior probability PT, and then you deliver and then the algorithm delivers the behavior change message. So what's delivering actually is the smartphone or the smart device or Siri. It delivers the behavior change message with that probability. So if a lot of evidence, the evidence is really accumulating that it's really worthwhile to send that message, this probability, the posterior probability that this is transferred is going to be high. So with high probability, the message will be sent. If the evidence is not in favor, then with very low probability. This is just a part of the MyWave study. Maureen has, it goes out on this side and it goes out on that side, but here's where the algorithm is, it's in red. And the algorithm, reinforcement learning algorithm is going to choose at each time whether or not to send a message based on 3 tailoring variables. And if you go to Maureen's poster, it's poster number 4. I don't know if you know that, but it's poster number 4. It's in room 121 on Friday at 1 p.m. Again, you can see, you can get a lot more information at our from these QR codes, and we're asking everyone to evaluate this workshop using this QR code. That'll happen after we have our discussion.